Hi everyone, this is Yin Lu, and I will be presenting our work optimizing decomposition for optimal claim verification, which will be published in ACL2025, collaborating with Nuisance, Hedan, and Mengjiang from University of Notre Dame. So first of all, let me give you some basic background. In the area of large language model, how people usually evaluate the factuality of a claim is to decompose a given long claim to multiple shorter subclaims and evaluate them one by one. So in this decomposition then verification paradigm, there are two basic components. One is decomposer and one is verifier. In our work, we define decomposer as a large language model guided by decomposition policy, which is typically the prompt, human-defined prompt to guide the language model how to perform the decomposition, what kind of rules and properties it has to follow. And famous decomposition policies include VecScore, WISE, and RND, and all of them will be used as our baselines in our experiment later. For verifier, we define verifier as a large language model with a verification policy. The verification policy could be retrieving relevant evidence during the verification process to help the verification. And also, the policy could be in context demonstrations to instruct language model how to perform the verification. With the decomposition then verification paradigm, one natural question arises: how does decomposition policy affect verification through subclaim? Especially in our work, we study the impact of subclaim atomicity. Mathematically, we define atomicity as the logarithm of number of atomic information in the given claim. And one piece of atomic information is an utterance or sentence conveying a single non-trivial fact. So intuitively, with higher atomicity, we should expect a claim or subclaim is more coarse-grained and information-rich. But does that mean that claim is also harder to verify? Or in other words, with lower atomicity with less factual information, does it make the language model more confident in evaluating the factuality of that given claim? And our answer is this is not always the case. We found existing prompt-based decomposition policies do not always generate subclaims with optimal atomicity, resulting in suboptimal verification results. You can see the figure at the upper right here shows that the verification confidence of the verifier peaks at atomicity 1. So that means the verifier here, instead Llama Sambi, prefers the input claim with 2 pieces of number of atomic information. But the example at lower right shows that the decomposition policy from VecScore, it always generates subclaims with atomicity 0. So it fails to generate subclaims that best evoke the verifier's performance, leading to suboptimal results. And to address this problem caused by the static decomposition policy, we propose dynamic decomposition, a novel framework to learn a decomposition policy tailored to the downstream verifier. And our approach is compatible with any existing fact-checking systems, with both decomposition and verification in large language model are given and frozen. To summarize, we have the following contributions. First, we found existing prompt-based decomposition policies do not always generate subclaims with optimal atomicity, resulting in suboptimal verification results. And unlike existing decomposition policies that use a single prompt call to generate final subclaims, we formulate dynamic decomposition as a Markov decision process that involves a sequence of decomposition calls. And at each step, the policy determines whether a subclaim should be decomposed, with the newly generated subclaims passed to the verifier that returns verification confidence change as a reward. Therefore, this formulation enables the problem to be tackled using on-policy reinforcement learning. And our third contribution here is we introduce a RL framework designed to learn this dynamic decomposition policy to bridge the performance gap between decomposers and the verifiers. The learned policy requiring only 4.73 million extra parameters, it outperforms baseline decomposition policies, improving both verification confidence and verification accuracy across varying verifiers, datasets, and atomicity levels. Here comes to our problem statement and the method. First of all, we formulate finding the optimal decomposition policy for optimal verification as a bi-level optimization problem. Specifically, give a decomposition language model D, a verification language model B, verification policy and a clan dataset with binary factuality labels Y. We aim to find an optimal decomposition policy, PyD, such that decomposed subclans can maximize the verification accuracy. The F here represents the lower level constraint, which observes the decision made at the upper level and optimizes its own policy pi accordingly. And the decomposer D here is the upper level constraint. It ensures that all subclans are generated by it under a feasible decomposition policy that is lower level optimal. And by formulating the problem as a bi-level optimization, we want to simultaneously refine the upper string decomposition policy and optimize the downstream verification task, ensuring that the decomposition policy is aligned with the verifier to achieve optimal overall performance. But bi-level optimization is known to be strongly NP hard, and the research has shown that it can be alternatively approximated using online stochastic approximation. Therefore, we propose our dynamic decomposition as an A2C style RL solution to approximate equation 1. To model the dynamic decomposition as an MDP problem, we have to first define few key components of it. First of all, state. We create an atom state at each step T to reflect the overall atomicity of current subclans, and each atom state is a d-dimensional vector. And we use the trainable gated recurrent unit to model state transition function, and in it we compute the information as the average conditional pairwise mutual information difference between the target subclan and its decomposed results. And that data information basically quantifies how much information is lost from each subclan after current decomposition call. And you can see the encoding C here reflects overall atomicity of all subclans in terms of semantics. So multiplying global decomposition embeddings by the local atomicity change, information change, preserves original semantics. We are reviewing hidden states regarding atomicity of current subclans. If you are interested in more information on how we compute data information, please refer to our paper where we detail key properties that validate our design. For actions, we only have two kinds of actions. One is decompose and the other is not decompose. For each atom state, the action is sampled from our decomposition policy, and our decomposition policy is trained to determine when to decompose a clan until achieving the desired atom state that maximizes the reward. Our reward is defined as the verification confidence change before and after decomposition, and the verification confidence measures how much certainty a verifier has in making a verification, which we found to strongly correlate with verification accuracy. This design encourages policy to perform decomposition when the verifier is more confident in evaluating the factuality of generated subclans. For the overall dynamic decomposition process, we utilize bridge first order. In other words, we prioritize the decomposition of subclans at higher atomicities. We perform binary decomposition for each clan at each step, and you can see the number in the node represents a sampling priority in the decomposition process for future decompositions. We first sample our sample subclans at the same atomicity level with newly generated subclans queued in a first in, first out order for future decomposition process for determining whether or not it should be further decomposed. And the other question we want to answer is why we use verification confidence. There are two reasons. First of all, it is because of lack of ground truth labels for newly generated subclans. That makes accuracy-based evaluation not feasible for evaluating verification improvement after each decomposition. And the second reason is we found a strong correlation of verification confidence with accuracy. You can see in this figure, irrespective of data sources, ethnicities, and even verifiers, verification confidence exhibits a strong positive correlation with accuracy, with 0.88 Pearson's correlation coefficient. Now comes to our experiment part. First, for the dataset construction, we consider the given human annotated atomic subclans as the base at atom 0, and from atom 0, we recursively merge subclans together to build clans with higher atomicities. We also decompose the base subclans to a lower level, atomicity -1, where subclans are partially tautological and trivial. So you can see in this table, each subclan is purposefully built to contain T to the power of atomicity pieces of information. And we used the following two decomposers in our experiment, Llama 3 Inst70B and the DeepSeek V3. And for our decomposition policy, we model it as a two-layer fully connected perceptron with a ReLU activation function with a total of 4.73 million parameters, and it is trained by PPO. For verifiers, we use a T53B fine-tuned on the fact score dataset for the factuality verification task, and a Llama 7B trained on supernatural instruction dataset, and a pre-trained and instruction-tuned Llama 3 8B model. And for verification policies, we use the following three verification policies. Retrieval retrieves relevant passages from a database as evidence. In-context examples provides verification demonstrations to instruct verification, and no context directly asks the verifier for prediction. Our first experiment finding is each verifier has its own preferred input density at which the verification confidence peaks. Even when utilizing the same verification policy, such as retrieval, different verifier language models exhibit distinct preferences, and vice versa. For instance, Llama 3 Inst-AB with a retrieval verification policy consistently performs best at adamcy 0 on both the ChatGPT and the Perplexity AI dataset. But fine-tuned T53B with retrieval verification policy retrieved its optimum at adamcy 2. And this observation demonstrates that the different preference for adamcy makes existing static decomposition policies like those demonstrations prompts hard to find optimal subclans that bring consistent verification improvement and optimal verification performance. We now compare our learned dynamic decomposition policy with four popular baselines on different data sources and verification policies. We found dynamic decomposition consistently achieved the highest verification confidence for the clans with adamcy 1 and 2, outperforming the four baselines by an average margin of 7%. We also evaluate dynamic decomposition on verification accuracy and observe a notable average improvement of 12% for clans from Perplexity AI with adamcy 1 and 2. We repeat the experiment with another decomposition language model, DeepSeek V3, and observe similar improvement in verification accuracy. We also did the ablation study for our dynamic decomposition policy, and we found two takeaways. First of all, we found decomposition exploration is effective for long-form text verification. We investigate whether a simple shallow model can capture the Adams data and find that reducing the network to a single layer resulting in lower verification confidence for decomposed subclans. Similarly, switching from binary to triple decomposition at each step, which reduces the exploration of subclans on different Adamsities, also leads to declined verification confidence. We also find that gradually removing clans of lower Adamsity from 1 to 3 from the training set negatively impacts verification performance, highlighting the importance of cross-Adamsity data for improving generalizability and the stability of dynamic decomposition. To conclude this paper, we first find that each verifier has an optimal Adamsity where its verification confidence peaks. Therefore, we introduce dynamic decomposition that optimizes clan verification by decomposing clans into verifier preferred identity learned via on-policy optimization. And our policy stands out for its adaptability to diverse verifiers and input clan identities, outperforming existing baselines while adding only 4.73 million parameters. If you have any other questions, feel free to reach out to me. Thank you for listening.